Greetings, my name is Matt Roscoe. I'm an assistant professor in the Department of Mathematical Sciences at the University of Montana, and I'd like to talk to you just briefly about why do we need derivio. The genesis of derivio came from a prompt that was provided at the National Council of Teachers of Mathematics annual conference in 2013 by Dr. Alan Schoenfeld of UC Berkeley. He provided this prompt, this, assessment item, as an example of the types of assessment items we might see in the near future as the field transitions away from a field that emphasized rote learning and procedural knowledge towards a field where students' ability to reason and make sense of mathematics is more appropriately assessed. I asked myself when I looked at this prompt, just exactly how would a student develop knowledge that would be useful in answering this particular question? And I thought to myself that the most appropriate way of generating knowledge about what it means to move and how that might look on a distance time graph would be through the collection of personal distance time data, some sort of a technological device that would allow us to track our own movement over time and generate graphs where we could remember how we moved and look at what that movement looks like on the plane when time is on the x-axis and distance on the y. That is exactly what derivio provides, and I'm looking forward to studying how interaction with this app will allow students to build their mathematical knowledge of distance time graphs. I think there are really three reasons we need derivio. It responds to the research in an area of difficulty, that is the misunderstanding of kinematics displayed in graphs. It supports curricular initiatives calling for increased reasoning and sense-making in math education, and it provides a platform where students can actively build up their mathematical knowledge. It's a tool for constructivist approaches to teaching. The fact that derivio responds to research is easily documented. Since about the early 80s, there's been a paper, at least one every 4 or 5 years, that have provided, evidence that students have trouble with kinematic variables when they're displayed graphically. That is, when position, velocity, and acceleration are displayed against time. So to give you an example, in 87, McDermott asked students which object is moving faster at time equals 2 seconds. As you can imagine, many students thought that object B was moving faster than object A because the value of its graph at time equals 2 seconds is higher than the value of the graph of object A at time equals 2 seconds. And they failed to incorporate a sense of slope as being the measurement here that is of interest when we're talking about velocity. Indeed, object A is moving faster. Monk in '94 collected data using this graph and asked questions about relative positions of the red and the blue car, and was able to show that students have great misconceptions about the movement of these cars when time is plotted against velocity. For example, when asked how are the red and the blue car moving after 5 seconds, many students said, well, the red car is moving away from the blue car because the red car's velocity is higher than the blue car. When we look at the graph, we can see that the blue car's concavity indicates that it's actually accelerating after 5 seconds, and so the blue car could be catching up to the red car as time marches forward. Lai most recently developed a tool for measuring students' misunderstanding of kinematic graphs. In this particular prompt, it's the only open-ended question that's part of this assessment. He asked the question, Gazelle trains for a race on a 100-meter field. To train, she repeats the following routine every 2 seconds. She begins her sprint 20 meters from the end of the field, sprints to the other end of the field, takes a short rest, and walks back slowly to her starting position. Draw a graph to represent how Gazelle could complete a 2-minute routine. They were able to classify the types of answers that they got. They got lots of answers that are similar to those graphs drawn in A and B, but only 1% of the students could actually provide a correct answer, one like that shown in C. Secondly, I think derivio responds to curriculum initiatives. The Common Core State Standards in Mathematical Content and Practice, which was released in 2010, is the definitive curriculum initiative in the United States right now. It divides mathematical content mathematics into 2 different areas. So there are 8 mathematics practices and 300 plus content standards. The real revolutionary idea in the Common Core are the practices, and I think that derivio gives us the ability to address at least 4 of these practices in mathematics classrooms. I think using derivio, students will be able to reason abstractly and quantitatively. They can talk about graphs, abstractly. Concavity and points of inflection could be discussed, but then you can go out and collect data that would allow you to reason about them quantitatively as well. I think derivio gives students the ability to construct arguments and critique the reasoning of others. That is, students can display their conceptions about kinematic graphs and then go collect data and critique whether or not their arguments are actually correct. Certainly, derivio is a tool for modeling with mathematics. It allows us to model our own movement using graphs of distance, velocity, and acceleration. And finally, it's an appropriate tool for mathematical learning. That if you have questions about kinematic graphs, this is the tool that you can use to learn about what it means when I plot my distance versus time, or my velocity versus time, or my acceleration versus time. The last thing I'd like to say is that derivio supports constructivist approaches to math education. Really at the heart of the reform movement in mathematics is this philosophy of radical constructivism, which posits that knowledge isn't passively received, but is actively built up by the cognizing subject, and that the function of cognition is adaptive and it serves the organization of experiential world, not the discovery of ontological reality. So at the heart of the Common Core and the reform movement in mathematics instruction is this idea that students no longer can sit in chairs and expect to learn when they passively receive information, but rather they have to be actors in their own knowledge construction, and certainly derivio is a tool for that particular approach to teaching and learning. So let's return now to the genesis of the derivio app, the question that was posed by Alan Schoenfeld in 2013 at the National Council of Teachers of Mathematics annual conference as part of his plenary address. And let's ask this question: how does the derivio app help students answer more successfully questions like this? I think that the answer is obvious, that the way that the derivio app could be used to help students construct knowledge that would help them answer this question is to ask them to recreate graphs like this, to simply give them the derivio app and say, I want you to recreate this 3-person race. Imagine the kind of discussions that would have to happen for 3 people to coordinate their movements so as to reproduce the graph that you see before you. I look forward to incorporating the derivio app in my introduction to calculus during the first week of the semester next fall. And I hope that you share in my excitement as I think about the future possibilities of mathematical learning now that the derivio app is available.